I'm Dave Gilbert, and I work for Red Hat in the migration sub-team of our QEMU team. And most of the talks tell you about great new things that work great and how everything just works. I'm going to tell you about why migrations fail. But first, I'd like to emphasize that actually they don't fail very often. For those of us who work on them day to day and spend our lives fixing migration bugs, you think they fail all the time. But actually, when you go out and speak to people, they say, well, actually, it works. And if you do hit problems, we've now got a troubleshooting page on the QEMU wiki to help you work through some of the more common errors. And if you hit one that isn't there, please let us know so we can add it. So that's great. They work. That's got to be good. The downside is that now people know that they work. People expect them to work every time. So what used to happen is that people would carefully plan migrations. They would tell everybody that there was going to be a migration, that they'd better make sure they weren't doing anything too critical. They'd plan it at a weekend, and it'd all be very carefully planned. But now it's fully automated. Your large clouds bounce VMs around as if you didn't know what was happening. The admins of the cloud don't even know what the VMs are running while they're migrating them. Automatic load balancing and host evacuations are very common. But we still need those migrations to work, even if the guest is rebooting or in the middle of an installation, or even if the guest has already crashed, because the admin of the cloud doesn't know that about their VMs, but they just want all of the VMs to move off this host that is on fire, or that they need to replace the power supply on, or they need to shut down. So let's start with some basic expectations that we can rely on for migrations. We need a good TCP socket connection between our hosts. We need working hosts that aren't otherwise failing. And when there's problems, we want some accurate error reports. Those are reasonable basic expectations. Of course, they're all completely wrong. One of the bugs I had last year was a bad NIC driver that just randomly lost 1.5 meg out in the middle of the migration stream. You find bug reports that hit on migrations that are MCEs on the host, bad storage, broken shared storage, all sorts of broken host configurations. And for some reason, migrations are really good at finding kernel bugs. You also tend to get very varied error reporting. So you'll get stories about how the migrations failed for this person, and only after a week of debugging do they admit to the fact that it was on a weird nested setup on a machine that only just about works. So the most common type of migration failure is a timeout. And this comes from a fundamental difference to the bandwidth we've got to deal with. Roughly, taking your modern Xeon to memory, you've got about 100 gigabyte per second of memory bandwidth. By the time you get to your PCI bus, you might have 15 gigabyte on a good day, and pretty much the fastest Ethernet you can get is about 100 gigabit. So there's a factor of about 8 there between the RAM bandwidth from the CPU and the rate at which you can stuff a migration stream across the network, even on a really good day. The reality is it's much worse. We can't saturate much more than a 10 gigabit link with the normal migration code. You can with the RDMA code. And if the CPU writes a single byte in a page, then you send the whole page across again. So the reality, once you're also sharing network bandwidth, is you might only have 1/100th or 1,000th of the bandwidth you can write to memory with to move the migration stream. So a busy VM just times out the migration. Similarly, rapid shared disk writes can have similar problems. We've added recently mechanisms to help you in those situations. Postcopy migration copes with very busy VMs, and auto-converge is a mechanism that throttles the CPU usage of the VM on the hope that it'll write to RAM less and less to enable the migration to complete. One thing to be careful of in management layers is to make sure that if your migration fails by a timeout or anything else, that you clean up. And for example, any shared networking goes back to the source host now that the migration has failed. We've had problems in the past where migrations fail, but then network configurations and things still think they want to move over to the destination. So before I go any further, it's useful to talk about the way our migration stream is structured. And there's not a vast amount of structure in there. There's a simple header that says, hey, we're a migration stream. It's got some version information and machine type information in now. And then we've got a series of what we call sections. And each section has a header which says, hey, I'm RAM, or hey, I'm this device, or whatever. And the data within that section, and then a marker at the end, the footer. And what we have is some devices are what we call iterative. So RAM is iterative, where we send the data for the RAM, and we keep sending the data over and over again until it converges. Most of the devices, say an IDE controller, just get sent in one section at the end. So each one of those sections would be, say, an IDE controller or one disk, or each one would have its own section. And those sections are named by typically the PCI device ID, so the PCI number. One of the critical things to having a migration work is to get your source and destination QEMUs configured absolutely identically. You're sucking the state out of one emulation and stuffing it into a destination, and unless they match exactly, you're either going to have some state that doesn't know where to go, or some state you've not provided. Or even worse, you can have some state that thinks that it's the state for one piece of information, but goes into a hole for something entirely unrelated. One of the critical parts to it is our machine types, and in QEMU on at least x86, I think on Power, and I think S390 now, we have version machine types. So you will have your PC 2.10 machine type for i440FX, and you'll have a 2.9 machine type. And what that means is if we need to make a change in how a device emulation works or the migration data, you can tie that change to a particular new machine type. That means that an incoming migration stream from a 2.9 QEMU configured with a 2.9 machine type could be correctly read by a 2.10 QEMU configured with the same 2.9 machine type. If we get it right, that is. It's very easy to screw that up and add a new field incorrectly that gets added to all of the machine types. And there are scripts. Amit has a script that helps look for changes in the migration data. But it's very interesting when you miss this. So if you add a field in somewhere and you don't notice it in the 2.10 release, say, you come along and try and fix it in 2.11, but find you're in the state now that if you fix it, you might now accept a migration from 2.10, but break a migration from 2.9. So it's very difficult if you don't find it soon enough. Another critical issue is device addressing and ordering. QEMU's command line ordering is in no way guaranteed. So if you create 3 disks or 3 USB devices, which devices they get assigned, which numbers they get assigned, unless you explicitly state it, is not guaranteed. And that's especially true with hot plug. That's great fun if you have, say, 2 USB storage devices, and you migrate them to a destination where the destination QEMU has associated those 2 USB devices with the opposite address, and the guest suddenly is accessing the wrong disk for the same data. One final one on this case is padding of ROMs. So let's say we take our BIOS, and let's say that you configured and built your C BIOS, and it comes out as a 64K ROM image. In your next build, in your next release, you add something, you fix something minor, and your C BIOS comes out at, let's say, 68K ROM image. You now have a problem that if you try and migrate a 68K ROM image into a 64K whole, it doesn't fit. So one of the things we do downstream in Red Hat is we pad our ROMs. So we pad, I think, generally to the next power of 2, which gives us plenty of room for growth. Finally, on matching source and destination, getting a matching source and destination CPU definition is critical. And that's actually quite hard. If you know that you, say, have a Sandy Bridge CPU, you could say minus CPU Sandy Bridge and all's good. Except that actually there are now lots of variations. So there are server variants of CPUs and a few different server ones with different flags available, so that no single name can cover them all. And there are other things that are less obvious. For example, if you have a machine configured with hyperthreading, the number of performance counters available per virtual core is half of that you have on a system that's configured without hyperthreading. And so if you try and migrate between them, you get a mismatch because the number of performance counters doesn't match, if you've enabled performance counters in your emulation. You also get new generations of CPUs that remove a feature. So for example, you might think that a conservative thing to do is choose the oldest CPU in your cloud. So let's say you've got a cloud, you bring a new latest generation CPU into your cloud, and you're stuck with an old one. Occasionally, CPU vendors will remove an obscure feature, but we can't then enable you to run with asking for that feature, because when the guest starts trying to access that register, it's non-existent. And what happens when you come along and put in the latest, greatest CPU into your cloud, which is newer than QEMU knows about? Which one do you pick? And that can be quite a difficult question to solve. So generally, ignoring some of what I said, the best thing to do is to pick a CPU type that QEMU knows about, that is compatible with all of the CPUs in your set of hardware. And at some point, you have to jump forward if you want your new features. Now, one of the other cases of failing migration, other than mismatches in configuration, is failures that occur while serializing or deserializing device state. So if you think about what we're doing, we have the serialization and deserialization, and the code that's in individual devices tends to do some checks. And these checks that occur tend to be more substantial than the checks that you do while you're normally running. If you do a check during an outgoing migration and you realize your device state is inconsistent, what do? Well, some device emulations abort at that point. Now, if you abort the emulation, people go, oh my God, the migration killed the VM, because the VM has died and all they did was try and migrate it. But you have found an inconsistency in your device state, so what do? If you do a check on the incoming side, that's a bit safer in the case that what happens there is that the destination VM doesn't run, but at least the migration fails cleanly and the source VM is still running, so at least the user still has their running VM with whatever critical workload they have on it, even if they can't migrate. My ideal scenario is I prefer that you don't fail the migration even if your device state is inconsistent. I prefer that you just error your device. I know there's people who hate that idea, but that's my preference because I never like migrations to fail. One of the critical things is problems of failing migration due to what the guest has done. So there's effectively two types of checks that can be done during serialization of a device. One of them is on your internal state within your emulation, and the other one is to do with what the guest has programmed your device to do. One of the things you can find is that the guest can have misprogrammed your device, and during the serialization, you throw that as an error. But that's the guest's fault, and you shouldn't stop the cloud admin migrating that guest to another host, even if that guest is kind of screwy because of the device driver in it. And sometimes these types of checks trigger erroneously due to the time they're performed. For example, if I migrate during boot up of a guest, while it's doing the most basic initialization of your device, will the device state be consistent enough to pass your checks? What about if I migrate during the BIOS? Or perhaps if I migrate from the installation disk of the OS, which has a different driver on it. All of these things come back to us as a migration failure, and then it takes quite a bit of digging to find that, for example, there was a new device driver just released onto the guest OS, and now all the migrations are failing. However, whenever you find any of these things in your serialization, please use error report. I'd like to be able to see in the standard error logs something that says this device is broken because this is wrong. That way, when I see a migration failure on a particular device, I can immediately see why that device failed. One tricky issue is what to do with conditional state. Now, what I mean by conditional state is data that is part of your device state that you don't always need to include. And there are effectively two types of reason for this happening. One of them is a piece of state that only happens in some rare configuration of a device. Another type of thing is where you realize that you forgot to migrate some state so that in the next version, next machine type, you add the extra state in. Now, there are two ways of doing this. And I'm assuming you're using the VM state macros. One of them is you can make a conditional field. So in this case, what we're talking about is a 16-bit integer, and we're saying that that 16-bit state will only be stored into the migration stream if bool func returns true. And that function can be as hair-raisingly complicated as you like, looking at lots of different bits of state. But it's very delicate. If your destination bool func doesn't agree, we read 16 bits of data off the stream when we shouldn't have, and those 2 bytes suddenly land up in the next field along, and it all gets horribly out of sync. Hopefully the section footer is inconsistent and you'll fail cleanly. It didn't used to, it used to just carry on, and if you're unlucky, you just get a dead guess. So ideally, try and avoid conditional data fields like that done that way. Because the alternative is subsections. Now, subsections are a named section within the device. And just like the named fields, you can make them conditional on anything you like. You can make them conditional on the machine type, a property of the device, the state of the device, whatever. But the nice thing about them is because they're a named structured addition, if you are inconsistent with the check, you get a nice error telling you that that subsection wasn't expected, and it all fails quite cleanly. You still have to be careful that if you want to maintain backwards migration capability, you never send that subsection for an old machine type. Now, what about testing your devices? Well, all of these conditionals and subsections increase the test load quite a lot. It means you now have to check that your migrations work when these subsections are present or missing. You've got to check in odd states that you might not have thought about, like an ejected CD-ROM or a keyboard with a full input FIFO. As I say, during migration, during firmware, or during a reboot, during a screen mode change, for example. And the OS installer disks tend to have simpler drivers on that are more conservative. Similarly, if you migrate a VM, the destination VM runs with the CBIOS or OVMF image that was running on the source host. Even if you reboot the guest on the destination host, it's still using the ROM image that it got from the source. So what that means is that you have to test your QEMU using your older ROMs as well as your current ROM. So if you make a release with a QEMU and this particular CBIOS, and you test them together, that's all great, but you've still got to test that if you migrate inwards from an old guest that had an old CBIOS image in it, that still works, because maybe your new device model doesn't work with the old CBIOS. Critically, you can never assume that you've tested all your OS versions. You see people come along and say, well, I tested on Windows version this and Windows version that, and I tested on 3 different versions of Linux. And always, a week after that happens, somebody comes along with the other version of Windows, or the other version of Windows that people thought was the same version of Windows, except that it's the one they got via that route, or had an update, or whatever. One specific thing to look out for is migration of PCI config data. PCI devices have a block of config data that contains all different sorts of information, all things to do with PCI Express setup, interrupt setup, loads of different things. And basically that config data has to match on the destination such that you think that your PCI device is configured in the same way as you specified it on the command line. If they mismatch for some reason, you'll get an error like that, and that's telling you that byte XXX within the config is mismatched, and there are masks to say whether particular bits are allowed to match or not. Typically what happens is that somebody fixes a PCI device because they realize they missed a feature out in that PCI model. You add that new feature, it updates a capability flag, and then when you try and migrate inwards, it fails. One thing, again, to look out for is some of that capability data is actually a linked list of capability blocks. That list has to be in the same order. You can't reorder it when you clean up a device, for example. And a really simple way to check is lspci-v in the guest should basically match between source and destination. Well, source and a new version. One problem you often get is you'll get a pair of errors like this. So the top error is what you see on the destination saying, I couldn't load it, there was an error. And you get the bottom error on the source, which said, I tried to write into my socket and I got an error. So who broke? Well, maybe it was the destination that failed, maybe it was the source that failed, maybe it was the network that was in between. If the network goes away, or say that you've tunneled your migration stream through something, then you'll get both of these errors at the same time, and you won't be able to figure out what failed, because neither side of the QEMUs had the problem. You can also get the top error if a device state loading, say a disk migration, fails with an I/O error. So that might not actually be a network migration stream error. But that can be quite tricky if you can't tell whether it was the source or the destination that failed first. Again, that can happen if your device state verification breaks on both sides. One tricky thing to get right is ordering and timing. Say that you're loading a state of a PCI device, and you're also loading the state of a PCI bridge or an interrupt controller. If the PCI device asserts an interrupt as it's migrated, is the interrupt controller that is going to receive that interrupt ready to handle it? And what that may require you to do is to ensure that the devices are migrated in a consistent order. For example, you might require that your interrupt controller is migrated before any of your devices that generate interrupts to it. And there's support for explicitly ordering the devices now. Most machine types actually get by due to implicit ordering in the order which devices are created. This is scary. and probably breaks when we least expect it. The other ordering and timing issue you get is what happens just after you've loaded the device. For example, loading a device, the device might have an emulated timer in it. When do you start that timer running? Well, the answer is not immediately in the code that loads the device state, because that timer might trigger before the migration is actually finished loading. And you certainly shouldn't be doing it using a physical timer, host-based timer. Doing it based on virtual time works because it doesn't happen until the CPU starts running on the guest. Other ways are you can wire up a run state change handler so that you defer starting your timers until the VM has started running. Also look out for that the management layers typically start the destination with -s. And what -s does is that once the migration data is loaded, QEMU doesn't immediately start the guest running. It gives libvirt a chance to reconfigure networking and storage. So again, that delays the point at which your device emulation actually starts execution. And you have to be careful of device state and things, timers and things that happen in that gap. And snapshots is the worst case, because a snapshot is a migration that goes away for 6 months while the VM image sits on the disk. I'm briefly going to talk about storage. I don't actually deal with storage migration much because it's quite separate from the core migration code. This is kind of the worst case, is that you might have a shared disk that's connected to the source and destination host. You can have non-shared disks, which are on the local file system of the source and destination host. And the worst case actually is maybe you have a failed storage device as well. And that's an interesting problem, maybe a full storage device or a storage device that's actually failed. One thing that we've had problems with previously is management layers misdetecting whether a storage device is shared or non-shared. So, for example, if you think that a device is shared, but it's actually not, then you won't bother doing a block migration. And when you start executing on the destination, it starts reading data off a blank disk file because nobody bothered to migrate the data. The opposite of that is actually worse. And the opposite is the case where you think that your disk is non-shared. So what you do is you start migrating your disk contents to the destination, but you've actually shared the disk image. And so you overwrite the disk image, which is shared by the data from itself going over the migration stream, and you end up with a hopelessly corrupt disk. That's basically what I said. There are some, especially with shared disks, getting the permissions and locking right on the shared disk is tricky because during migration, you've got to hand off who's actually owning that disk. And in recent QEMUs, there's some explicit locking code in there. But other than that, you have to be careful of some storage devices just don't like having a source and destination accessing the same device. One other issue with storage devices is that At the end of the migration on the source, you have to drain all of any outstanding writes have to be pushed out to the storage device. And if you have a guest that's heavily performing storage writes, that last piece of writing can delay the end of migration and increase the downtime substantially. That's quite tricky to fix. One way is to just throttle the write bandwidth. But the worst case of this is actually if at that point your disk fails and you're left trying to write out your blocks before you migrate, but you can't. There's a complex interaction with the NBD-based block migration, which actually we've just, as of 2 days ago, changed that to allow the management layer to pause the main migration code and allow it to tear down any block migration using NBD before allowing the migration to finish. There's also the old QEMU block migration code. Please don't use it. Use the new NBD stuff. And finally, on storage, there's caching. If your source is caching storage data and you migrate to the destination and you have write data that hasn't actually made it to the shared storage, and you start running on your destination before that write data has made it, again, you end up with something that's inconsistent. Typically for POSIX shared storage, we say you must use cache equals none on your storage devices. For other storage, e.g. Ceph, it depends on the particular library you're using as to which cache equals option you need to use. So my final 2 slides are, an important question is, did the migration actually work? Well, it's normally, most of the failures are fairly obvious. You get an I/O error and, well, it definitely didn't work. However, that check to see whether a migration has worked used to be fragile because all it used to depend on was getting the TCP socket close. And if we got the TCP socket close on the migration stream, the source said, yep, that's good. However, that's quite fragile in terms of if your device state loading fails, that device state can be in the last 4K block that's in transit on the network. And you get a race condition about whether or not both sides agree it failed. Peter recently added an explicit check at the use of the return path, even in pre-copy. So we now at least get something that says, hey, it worked. You can get failures of networking or storage in the gap between the point at which the migration stream finished and libvirt starting the destination. So if your networking failed at that point, or you failed to reconfigure a switch or a SAN, you have a problem. And the hardest problems to deal with are when the migration has apparently all worked, but the guest is just dead. Those are really nasty to debug. Typical causes, missing interrupts, timers that don't agree in either direction, or corrupt RAM and storage. That's the worst case for debugging. And this is my final slide. So okay, you migrated, the guest is still working. Are you sure everything's okay? Well, is the guest really okay after migration? What happens if you reboot after you migrated? That will cause you to take different paths through your device code. And again, it will cause you to use your old firmware version on your new destination QEMU. You can get odd downtimes. So again, the migration has apparently worked, but networking disappeared for 5 minutes. You didn't get any errors, but people said the guest doesn't respond. So, checking that the RARP advertisements for networking works is a good case of that. Similarly, Postcopy, if it never actually gets the request back to the source, it will complete just very slowly. Is the performance on the destination the same as the performance on the source? Did the transparent huge pages rebuild correctly? Is your NUMA placement correct? And are all your disk caching correct on the destination? And finally, to wrap around to the beginning, will it migrate a second time? And, one of the common tests we have is what we call a ping pong, where we just migrate it back and forward between 2 machines and just leave it going. And if it survives over a weekend, your migration probably works. Thank you. Any questions?
Hello, I have a question regarding your suggestion to use cache equals none. Is this just a missing F data sync somewhere, or is this a fundamental issue that we cannot solve by putting proper barriers in the code somewhere?
My understanding is that with NFS, there's no way to ensure that all of your writes are synchronous on the source, and that you're then guaranteed to get them on the destination, except with the cache equals none setup. So that's my understanding of that. But I know that every time we ask this question, we get a different opinion from someone, and then we fall back to saying that the only one that everybody agrees is safe is cache equals none. So yeah. Certainly the other cases, the Ceph and the like, are the opposite case, which is harder.
So as far as I know, the real problem is not about the getting the data flashed on the source, which we do fsync, so that should be fine. The real problem is that if we have on the source data already in a kernel page cache, there's no safe and reliable way for us to invalidate that cache, so that reloads the data that the source has synced. So it can happen that the destination will still read the stale data that it already had in its cache. That's a real problem.
Which I think one of the answers here is if there's a friendly kernel person who would like to give us that ability, that would probably help a lot.
Hello?
No.
Yep. Nope. Ah, there we go. Amazing. Yeah, you had some really great suggestions about how to do things like subsections and what the right and wrong way to write device VM state structures is. How would you feel about maybe writing some of those into a patch to docs devel migration.txt?
Yep, definitely.
I think if we can write that down, it will be much easier, because then we can just point people and say, look, here's how we suggest we do this. I think that would be great.
Yeah, I mean, one of the difficulties, so certainly pushing people to use subsections is something we've done for a while. Some of the other ones are, yeah, there's certainly a set of best practices which should probably be written down in there. Definitely.
Do you have any hints or tools for helping in debugging the cases when the guest hangs because of missed interrupt or something?
A good set of food to work with and some relaxation and something to keep you sane, because it's really hard. There's various cases. For example, we know Windows doesn't like a difference in timers. So if your host clock is different on the source and destination, that's a known case, we know it breaks. But missing interrupts, you just have to follow the interrupt through and find out where it went. But that's really difficult because it's so dynamic and you can't repeat the state on every time you run. A lot of these cases will fail as in it fails about 1 in 10 times type of things when it loses an interrupt. And those are really hard to deal with. One of the things for corrupt memory contents, I tend to migrate something like Google's Stress App Test, which is really designed to test whether real physical hardware has broken RAM or broken hardware that's corrupting memory contents. If that passes and your memory on the destination comes out the same, then you probably migrated the data correctly. But yeah, broken, when it hangs like that, that's just really hard. The best thing is to try and isolate if something changes it, like if I use a different network device or if I turn that feature on and off, does the problem go away? You know, just to try and isolate it to one case. But often these things are the worst case of bugs you have because they may only happen on a particular machine with a particular speed or a particular configuration. And that's the worst case migration bugs we get. Thank you very much.